reflections. Learning goals here: to define reflection, a perpendicular bisector, a mirror line, and a line of symmetry, and to reflect figures over a mirror line. So we have an example of reflection here. Okay, just like you would look in a mirror. Now let's talk about it. So what is a reflection? We encounter reflections every day as we look in a bathroom mirror, peer into a pond of water, or glance at the traffic in a car rear view mirror. Okay, we know that when we look at a reflection, okay, it's reversed. We know that just from living our lives. All right, well, that's going to happen the same in math. Okay, so we have an object reflected over a mirror line, and it becomes this red image. Okay, the shape is not different, it's just flipped. Okay, so very important, nothing about the size of the shape changes. Okay, it's just flipped over a line. All right, this is coming from an investigation. I'm just going to give you this information here. Okay, and this is something that's better seen in person. But the image is as far behind the mirror line as the object is in front of it. Meaning, okay, if I take this black triangle as my object, this red one's my image, this distance it is from this mirror line is the same. Okay, it doesn't get closer or farther away, it stays exactly the same. Point C, A, and B are all the same distance away. Okay. The line joining any image point to the corresponding point on the object is at right angles to the mirror line. Meaning, okay, if I make a line here and with my mirror line, okay, this becomes a right angle. Okay, it has to be, because it has to be directly perpendicular to the mirror line, always. All lengths and angles are the same size in the image as they were in the object. Again, this is because the shape doesn't change. So this angle is the same as this angle. This angle here is the same as this angle here. Okay, this side is the same length as this side. This side, okay, our B prime C prime side is the same as our BC side. All right. All points on the mirror line are invariant, which means they do not move. Okay, all points on the mirror line are invariant, meaning they do not move. So if I had a shape that was like this, and it's on the mirror line, well, then my next shape would be a similar one, but those points wouldn't flip because they're already on the line. Okay, the mirror line is a perpendicular bisector, meaning, okay, it goes directly perpendicular. So we have parallel and we have perpendicular. Okay, of the line segment from any point on the object to its corresponding point on the image. Well, that's why we get these right angles. Okay, because it's perpendicular, okay, we will get right angles. All right, so let's look at some examples. Reflect the figures using the mirror line. So our mirror line in this is going to be this green dotted line. So we just have a basic coordinate grid, or sometimes we call this the Cartesian plane. Okay, same thing. Okay, so we have our y-axis and our x-axis. So I'm going to flip this blue triangle. Okay, I'm going to flip it over this green mirror line. Okay, so what can be helpful if it's not labeled before is to label each point. So I'll call this A, B, and C. Okay, I notice A is 1 away from the line, so A prime needs to be 1 away from that. Then B is also 1 away, so B prime should be 1 away. Okay, notice the up and down's not changing, just over the line. And then the C is from our line. It's 1, 2, 3 away, so from this line it should be 1, 2, 3 away. Okay, and we could connect our triangle, label it, and there we go. This has been successfully flipped over our line. It's been reflected over the line. All right, let's take a look at using a shape that doesn't have nice and neat points. Okay, so when you have something like this, and let's imagine this did come up and touch here. We can just call this A. We can call this B. I'll switch colors here so we can see it. Okay, I'm going to, from point A, I'm 1, 2, 3 away. Okay, so I need to go from here 1, 2, 3 away. That's my new A prime. B is 1, 2, 3, 4, 5, 6, 7 away. 1, 2, whoops. 1, 2, 3, 4, 5, 6, 7 away. Now, okay, we know those are going to connect. And for up here, well, we can just take a good guess here. This is, here we could call that C. So that's 1, 2, 3, 4, 5 away. So 1, 2, 3, 4, 5 away. That's our C prime. And because this is a rounded shape, okay, we can just do our best here to make that curve. All right. So you can see it can be tough when we have curved. You just have to do your very best. But in theory, okay, you could take this exact point and map it over here. Now, that's a pretty standard line of reflection, just a vertical line. Okay, what if we had a horizontal line like this? Okay, well, same thing. So let's do this triangle up here. And we're going to flip it down over here. So B is, let's just go with our closest points. So B is 1, 2, 3 away. So I should be 1, 2, 3 away. C is also 3 away. So this is B prime and C prime. And A is 1, 2, 3, 4, 5 away. 1, 2, 3, 4, 5 away. And we connect our points. Boom, boom, boom. We've successfully reflected back over this line. Okay, we could do the same thing here. Okay, so this is, from here I'm 1, 2, 3, 4, 5, 6, 7 away. 1, 2, 3, 4, 5, 6, 7. A prime. Okay, now B is also going to be 7 away, and it's 1, 2, 3, 4 away from B, from A. 1, 2, 3, 4. And C, this top of our curve, is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and let's just connect our shape. And there we go. We've successfully reflected it over here. Now, sometimes you might get a line of reflection that is not as quite as friendly. You might get something that looks like that. Okay, a diagonal line. And for our purposes, I'm going to clear this, and let's do this blue triangle over a diagonal line. Okay, so we have this triangle over a diagonal line. Well, we're going to do the same thing, except now we're going to have to count in 2 different ways. All right, because we know B is this far from here. Okay. Well, because these are going, this is a slanted line, we don't know exactly how far this is. Okay, what we can do is count in 2 dimensions. We can go count this distance and this distance. So B is 2 up and 2 right. Okay, so we need to go 2 down. And we're not going to go 2 left. We're still just going to go 2 right. That's our B prime. C is 2 up and 4 to get to the line. Well, we're going to go from our line, down 2, over 1, 2, 3, 4. And A is going to be up 4. So we're going to go down 4. And it's 1, 2 to here. So down 4, over 2, A prime. We can connect. Oops. Let's bring it back. And there we go. So we have taken, now we can clear some of this off. So we have taken this triangle and reflected it, okay, over this diagonal line. And this line actually has a special equation, okay. If we put this in y equals mx plus c form, well, our y intercept is 0, so y equals mx plus 0. And our slope is up 1 over 1, up 1 over 1. So our m is actually 1. So if we plug that in, we get y equals 1m plus 0. Okay, and now let's simplify this to, or not 1m, 1x plus 0. So if we just simplify this, we don't need a 1x and we don't need the 0. Y equals x. So this line right here is the y equals x line. We can see that when x is 1, y is 1. When x is 2, y is 2, and so on. Now, we can reflect over an axis. So sometimes your line of, your mirror line might just be the axis, like in this example. So reflect this figure over the y-axis. So you can, if it helps, you can make it clear. And go ahead and pause the video and try this. All right. So I'm going to label each of these A, B, each vertex I'm going to label something C, D, E, and F. This is to make sure I do every single point and I know exactly where they are. So A is 1 away. It's not A prime, it's just A. So A is 1 away. B is 1 down from A and 1 away. C is 2 away from this, so 1, 2. Okay, and we can connect as we go, if you want. D is 1 down from C. D prime there. This is a straight line. Let's just leave it for now. Okay, D prime. E is 1 away from D. E prime. F is 1 up from there. F prime. And then these F and A connect. Okay, and there we go. We've reflected this figure over the y-axis. Okay, so a line of symmetry is very similar to reflecting, and in fact it is a reflection but just kind of doubled up. So a figure has a line of symmetry, if it can be reflected in that line so that each half of the figure is reflected on to the other half of the figure. The best way to think about this is if I had a piece of paper and I folded it in half, okay, and the top half perfectly went over the bottom half, so you folded it just in half, that would be your line of symmetry. And we know with paper, okay, we could fold it in half, okay, from top to bottom or from right to left. So both of those are lines of symmetry. Okay, so we have a triangle here, an isosceles triangle, meaning two sides are the same. So if we folded this triangle over this line, we took this point, we moved it up and over to here, it would look exactly the same except reflected. So that's a line of symmetry. So for instance, we have a square. If we fold it in half, we could fold it like that, and that would line up. We could fold it this way. We could fold it from corner to corner, and we could do the other corner to corner. It does not count saying I can fold it this way and I can fold it back down this way. That's just one line. Okay, so just if you imagine a piece of paper, it's the number of folds in that paper. So for our piece of paper that's a rectangle, I couldn't fold it diagonally this way because I would have an overlap, and you would know that. Go ahead and try it. Try to fold just a normal piece of paper diagonally and see if it lines up perfectly. It won't. Okay, so we're going to draw all the lines of symmetry for our figures here. Okay, so remember, it's just if I could fold it over each other. So if I took this pot and I folded it from top to bottom, okay, that's not going to work. I have this extra bit on top. It's a much different shape on top than on bottom. But if I look at left to right, it looks the same. So I could actually, this is a line of symmetry right there. If I took this side and I folded it over, that would work just fine. So that has one line of symmetry. Okay, let's take a look at our parallelogram here. Okay, is there any way I can make this work? If I fold it like here, is that going to work? No, because when I fold it back over, okay, this little edge is going to stick out. So it would fold over and it'd actually look, we'd actually make a shape that looks more like this if we folded that over. So that doesn't work. Okay. If we folded it like this, the same thing's going to happen. Okay, and we'd actually get a shape that looks like, yeah, like this. And that doesn't work either. So take a think. Okay, so you might think, what if we folded it like that? Well, again, if I folded it like that, I would end up with quite a different shape. It would fold over and it would extend out to something. It would come up here a little bit. So no, that wouldn't work. In fact, this shape has no lines of symmetry. No lines of symmetry. Okay, this one has one, this one has none. Now take a look at C. What do you think? Okay, this right side looks the same as the left side. If I cut it in half, would that work? Yeah, that would work. I could fold it over that way. Okay, what if I could I cut it top to bottom and fold it that way? Yeah, that would fold back down. Could I go diagonally, like maybe through this? No, that wouldn't work. Could I go like this? No, that one wouldn't work either. So this has two lines of symmetry. So for lines of symmetry is, just imagine, okay, the more equal the shape is on each side of that line, okay, that's how you're going to determine if you can make a line of symmetry. Now, just because I have an equal area here doesn't mean my shape looks exactly the same. Now, because I have to reflect it over, and remember, when we reflect it over, even though the shape doesn't change, it is going to change how it looks. Okay, just because this shape is the same as this shape, okay, it does look different. Okay, and we can see that in all of these. Our hypotenuse faces this way, this hypotenuse faces this way. Okay, same shape, but it looks different.